So if t is an operator, then you can compose it with itself, and we'll call that t squared. And so this means that powers of t are defined. And then since the L of v is a vector space, then we can also take linear combinations of powers of t. And so things like 2t minus 3t squared plus 7t cubed are also going to be well-defined operators on L of v. And so this is why people like operators, because you can do this kind of stuff. And so we'll see we can actually apply polynomials to operators. So let's define t0 to be the identity operator, and for invertible t, we'll use the inverse notation. T to the minus m is the same thing as the mth composition of the inverse with itself. Okay, and then the usual exponent rules for algebra apply. So Tm, Tn is going to be t to the m plus n. And you can see that one because the left side says, write down m copies of t and then n copies of t. And the right side says, now you have m plus n copies of t. So there's no surprise there. And similarly, if you have tm raised to the power n, this is t to the mn power. Okay, so as I mentioned above, this allows us to apply polynomials to operators. And I don't know what the correct preposition there is. If you apply them to operators or on operators or whatever, you can take functions of operators. Who knows? One of those. So if we have a polynomial, so if p of z is given by a0 plus a1z plus a2z squared plus so on and so forth, a m z to the m. So if this is some polynomial over f, then for an operator on v, we define p of t to be a0 times the identity. That's our z to the 0, right? So there was secretly, let me write that in here. Here's z to the 0 power and z to the first power, etc. And then a1 t, a2 t squared, am t to the m, which will again be an operator on v. Okay, so we can do all sorts of interesting stuff with this. So for example, if we take d to be the derivative operator on the real polynomials, so dp is the derivative of p, and we have some polynomial p of x is 7 minus 3x plus 5x squared. Whoops, that was a pretty lousy 2. Plus 5x squared. There we go. Okay, so then p of d is going to be 7 times the identity minus 3 times the derivative operator plus 5 times the second derivative operator. So P of D applied to y equals e to the x is a way to encode the ordinary differential equation 5y double prime minus 3y prime plus 7y equals e to the x. And so it turns out that this becomes a much handier notation for dealing with differential equations, especially in partial differential equations, when you look at polynomials in several variables and you might have a ddx going in one slot and a ddy going in another slot, and so on and so forth. But anyway, so then let me clarify something here, and that is what we're looking at is for a fixed t, the application to t, or evaluation of the polynomial on t, so p getting mapped to p of t, this is a linear map from polynomials to operators, right? This is not the same as fixing a polynomial p and looking at the map t goes to p of t, which defines a map from the operators to the operators. In particular, this one here is going to be nonlinear, except in the case when p is just scalar multiplication. Okay, so the main idea here is that the polynomials, this guy p of f, is more than just a vector space. It is an algebra, right? Because we can multiply vectors together in p of f. And so this idea, we touched on it before in 3a6 and 3a in the examples. So you may wish to go back and look at that briefly. But the way multiplication is defined is just pointwise, and that carries over to operators as well. So if we have two polynomials p and q, then the definition of the product PQ, well, you define what PQ is by saying what it does to something Z. And what it does to Z is it does the product of P of Z and Q of Z. Right? So then for some operator, we have P of Q applied to T is the composition of P of T and, or the product of P of T and Q of T. And since T commutes with powers of itself, PT QT is going to be the same thing as QT PT. And now again, notice that this is not the same thing as saying something like P of S Q of T equals Q of T P of S. Because that in general is not going to be true.